I still hear a little bit of exclamation. Oh, we're on our calculators though.
I'm explaining it because
Okay.
I didn't have. Okay. No, I'm not. See, this is the
Okay. On each of these functions, first one, what part are we zooming in on and checking out for this question? Which part? For the first one. Right here. He's our most important guy. Why?
Because it has A and N.
It has A for the leading coefficient, and it has the highest degree. So we know right here that, in essence, with your notes, A is less than 0 if you were looking at it that way. The leading coefficient is negative. And we have a cubic function, which would be an odd degree, right? Okay. So, what's a normal cubic look like again?
Like the thing, sort of.
Visualize, my visual people. So what's a negative one going to look like? Z. Something. So couldn't we kind of, before we even stress about writing it in and making it look nice, couldn't we just do a quick like, oh, it's something like that? Then use that. Okay, so this is the normal one. Negative means flip. Use this to answer these questions. What is going on to my function as I go to the right? Yeah, we can either say it's falling. That's one way that the book might use, which is true. But there was this, I probably shouldn't use arrows now that we know that arrows actually mean something, huh? Falling, or what was the snazzy way of writing it yesterday? What are the y's approaching? Y's, f of x, are approaching what? Negative. But the idea is that the graph is falling. That's the idea. The notation says the y's are going down. Does that kind of make sense? Now, how would we answer going to the left? Rising, good. That's the idea. And then how would we put it in our snazzy notation? F of x2, or approaching or going towards. Infinity. Yeah? Okay. Now, technically, before we move on, isn't there a snazzy way, a notation way of saying to the right that we talked about yesterday? We did at the very end. Yeah, Ashley. X is approaching. Good. Positive infinity to the right. And so then, Tyler, if I'm going to the left, X would be approaching.
Negative infinity.
Perfect. So that's the snazzy way of saying to the right. Because the x's, remember, x's are along the x-axis. As x's go to positive infinity, get bigger, 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 I'm going to the right. And as x's go negative numbers, more and more and more negative, x approaching negative infinity, I'm going to the left. Does that make sense? Now, let's go to the next one. What's the most important part of the second function? What's A? True. And so it's positive, right? And then what kind of function? Quartic, which means a degree of 4, an even degree. So without even stressing, and without knowing exactly what all the graphs look like, whether or not they're like weirdly skewed or not, whether it's a W, whether it's a U, I can still say, well, it's kind of like that, right? At least the ends are like that. That's all I care about, right? The ends. So as I go to the right, what's going on? Rising. And as I go to the left, what's it doing? Rising. So I could say for both of these, rising, rising. And then I already hear you guys trying to do that snazzy notation, which is perfect. So then f of x approaches, and f of x approaches. Let me get out of the way. If it's rising, where are the y's going? The y values are going positive, right? And specifically positive infinity. It's just going to keep going up and up and up. Yeah? Now, if you guys want to see what the graphs actually look like, there's some funny stuff going on in between. But do we have the to the right and to the left down? Yeah. And to the right and to the left down? Yeah. in between that's the funny stuff, and we're going to have to kind of experiment with that. Remember, without calculus, we can't do this perfectly, but we're just kind of getting an idea. And this, the leading coefficient test, is about getting an idea about the ends.
So say I'm doing the x to the fourth.
Uh-huh.
Can I write my answer like if I'm doing the right? Can I write it x is approaching infinity and f of x is approaching infinity?
Add a little word, as. It's kind of like we need to make an entire thought. So as x approaches infinity, which means as I go to the right, comma, f of x is approaching infinity, period. Does that make sense?
Yeah.
So I want you guys to take literally 15 seconds to check your last one and see if you agree based on what we've done. Take a second, or 15 of them, to reevaluate what you put for the last one. And does it still make sense from what we've done? We'll give you another 15. I'm just going to start filling in, not even talking. You guys can check and see if you agree. Yeah? So then if we were to write that, what would you guys put? F of x is approaching positive infinity. And f of x is approaching for following negative infinity. And let's see if our graph agrees. Now what have we not figured out again? The middle. We haven't figured out the middle. We haven't even figured out exactly where they fall, because all of them seem to be around the y-axis. But we have figured out the ends. Is that okay?
Yeah.
Is the new notation seemingly making sense? Yeah. What does that little arrow mean? Approaches or goes towards. Heading, but approaches is the best mathematical term. Or English term, I guess. All right, let's keep going. Back in your notes. Good job, good job. We got to practice the leading coefficient test, which was one of the big clues from yesterday. Let's see what else we talked about yesterday. Polynomials are all continuous. You can draw them without picking up your pencil. Smooth turns, so you always turn in a curve, not like at a sharp point. Like imagine those old pictures that we did, the whole where you connect the dots, right? And sometimes there were like little problems that you had to solve, and then you connect the dots and then make whatever picture is there. When you were younger, you like those pictures? You like go from 1 to 2 to 3, or like 2 to 4 to 6, or you like connect the dots, yeah, and make the picture. When you were younger, wasn't the picture kind of like, and like you could see it, right? Some people would try rounding because they could tell where it was going, and they might make a prettier picture. Kind of the same idea with polynomials. If you are connecting points, you're always doing it in a rounded fashion, not in a sharp point. Anyway, that's what that clue is about. And then we did leading coefficient test. Now we need to talk about zeros. And to be honest, this is kind of a scary topic, but not in this section.
Okay.
Some of you last year might be like, oh yeah, we had to kind of figure out how to factor cubic polynomials and quartic polynomials. Maybe with like some synthetic division. Or some remainder factor theorems and figure out all the possible different zeros and subsets. But that's not this section. That's not this section. That's the next section. Matrices. Matrices are for solving like XYZ equations or ABC equations. Still useful, but different application. Ricky.
This mostly changes from or for.
Like, where?
Under turning.
Oh, from. It is from.
There's something, okay.
Yeah, hang in there. Hang in there. Okay, a polynomial has at most n. Wait. Who's n again? Do you remember?
N is the number,
What's the snazzy name for the highest power of a polynomial?
Degree.
Degree. So for a cubic, the degree is 3. For a quartic, the degree is 4. For a quintic, the degree is 5, etc., etc. So when I say a polynomial has at most n real zeros, if I had a cubic, the degree is 3. How many zeros at most will a polynomial have?
Oh wait.
Yeah, n, so 3. If I had a quartic, that means the degree is 4. It would have, that polynomial would have at most 4 real zeros. And by zeros, what do I mean again? Do you remember? Where it touches the x axis or the x intercepts, right? Zero is just a snazzy word or name for x intercepts. Now, I actually want you guys to put parentheses around n minus 1 just to make it a little more clear. Once again, at most, n minus 1 turning points. And let me show you a quick example of a turning point. If I was to give you just something basic like y equals x squared, we know its graph. It's positive, so it's facing concave. Jason, concave. Up like a cup, yeah? How many turning points does this function have? Just one. What do I mean by turning points? Remember how we read the graphs left to right? What's it doing? Decreasing and then increasing. It turns. It changes from decreasing to increasing. It has one turning point. Does that make sense from what we just wrote? A quadratic has, take n, take away 1 turning point. At most. Why do I say at most? What if I was to use x cubed? Well, it could have 2, but couldn't it also have none? So it could have none. Or a cubic function could have how many?
2.
Up to 2. Does that kind of make sense? So we say at most because it could have, a cubic could have up to 2 turning points, or it could have none. Depends on how stretched it is. Now, what do you notice about turning points? Yeah. See why I wrote that? If you have a turning point to a polynomial, it's either going to be a relative max or a relative min. That's relative is a snazzy way of saying even though it's a max here, it might go higher somewhere else. That's just why we say relative. But turning points will be at maxes or mins. And Ricky, what I was indicating here is they will occur when the function changes from increasing, see it, to decreasing. And that will technically be, round it, that'll be a max. Or from decreasing to increasing, and that would be a min. And these are just the arrows that are showing you the increasing, decreasing, etc. So that's what I mean by turning points. Now, if I come back to these examples, and let's just say I said it was an x squared polynomial. Let's say it might have more stuff than just x squared. And let's say it's an x cubed polynomial, so it might have more stuff than just x cubed. Let's go back to the zeros for just 1 second. How could this parabola have 2 zeros? If the x-axis did what? Yeah, if the vertex is under the x, would that make sense? How many zeros would it have? 2. How could it have, well, it said at most 2. Could it have 1? What if it crosses at the vertex or with the vertex? And this is the x-axis, right, and showing you where it could go. Could it have no zeros? Struggle. So depending on the polynomial, it depends on how it's been shifted up or down as to whether it's going to have 2 or 1 or none for a quadratic. I want you guys to look at the cubic for a second. How many different types of zeros could it have? Could it have none? Imagine drawing a line anywhere. Can it ever have no zeros? Yeah, it's going opposite ways. It's going to have to hit the x-axis some way. So we'll say, okay, if it hits down here, right, it's just going to have 1, but it can't have none. Could it have 2 zeros? How?
No. If it hits the vertex of the top of one line.
If it hits a vertex, like at a vertex, yeah, it could have 2, see? But how many? What's the most it could have?
3.
If it hit, right, if it went through each of the little branches, it could have 3. And how many zeros could that one have? 1, 1, 1, 1, 1. He's boring, only 1. But if we have more than 1 0, then it must be one of those curvy types. Anyway, it's kind of showing you what I mean by at most and what I mean by zeros, x-intercepts, and turning points, maximums, minimums. You guys already wrote this down, finding zeros. And I said 2 different ways, factoring out common factors, factoring the grouping way, or if that doesn't work, maybe the quadratic formula or completing square. But what I have not written down yet is synthetic division, remainder factor theorem. That's a whole section in and of itself, which means the ones you're going to see in a section are easier for some reason. The ones you're going to see in this section are easier for some reason. Go ahead, factor that puppy as far as you can. Factor him as far as you can. He's technically a 4th degree polynomial, but totally factorable. Without any complicated steps or procedures. Because there's a greatest common factor or 2 or 3. Is anybody done factoring yet? Just a couple. These are still working. But what did hopefully most of you see to pull out? What's in common between those two?
Negative 2x squared.
X squared. Great. Why'd you pull out a negative? It was a great idea, but why'd you do it?
Because then A would be.
We don't like negatives in the front if we can avoid it. So then if there is one in the front, we try to take it out, right? And then we end up with x squared minus, did you do it properly? 1. Careful. Whenever you factor, you can always double check by distributing back in and seeing if it matches, right? Can we keep going?
Yeah, we did.
Oh yeah, we can.
Sadly.
Sadly, doesn't actually make it easier.
Sorry.
It's okay. You're allowed to be honest. As long as respect is still there. And hopefully I can be the same back. How do I find zeros again? You're trying to solve for the zeros already, but just in essence, what do we do to find the zeros? Set the whole thing. And then when I have factors equal to 0, I set each one, technically, equal to 0. But a lot of you guys have learned that there are shortcuts to solving, so you don't necessarily need to write them all out, right? For instance, x minus 1 will be 0 when x equals positive 1. X plus 1 will equal 0 when x equals negative 1. Just a few of you might have forgotten the first one. When will this one equal 0? X has to be 0 or else, yeah, it's not going to happen. So how many zeros do we have? 3. And technically, don't those 3 points, or those 3, I should say, x values, don't they represent actual points on the axis where my graph is going to hit? So not only did we find the zeros by factoring, but we also found 3 points to our graph. Hey, wait a minute. This is a 4th degree, right? How can a 4th degree hit in 3 places? Yeah, it can't be this, right? That's not going to work. That's only 2. So it must do like a loopy-loop? Like a W? Ooh, nice. So it's going to be one of those, but the negative leading coefficient means, look at all you guys know already about graphs. Craziness. And more specifically, it can't be there. Can't be there. Where is this going to have to hit? You see it? Because the only way, this is going to hit twice if the x-axis was here. It's going to hit 4 times if it's up here. Only twice if it's up there. This is how it's going to hit 3 times. So what's the maximum number of turning points? 3. And if we check the actual graph that we just kind of figured out visualizing, does it have all 3? Yeah. You see it? There's 1, there's 2, there's 3. Now, will every quartic always have 3 turning points? What's this little note at the very bottom? You guys saw the word multiplicity last year.
Oh, no.
No?
No, I did.
I think you did. You probably just forgot about
I
it.
said no.
Repeated zeros means what? Aren't there technically x times x?
Yeah, that's true.
Aren't there technically 2 factors here? X times x. There were like 2 separate ones, but we put them all together because either one is only going to make 0 if it equals 0. So there was only one. There was only one negative one that came out, but how many zeros technically came out? Which is why we say a repeated 0 sometimes occurs when you're factoring, and when a factor is raised to a power like x squared, we can say it's 0 has a so just this one, has a multiplicity of, you see it? The power is the multiplicity. So since x is squared, it's a multiplicity of, we'll write more a little bit about that in just a slide or 2. Okay. All right. I'm going to give you guys a second to write down this page. This is kind of my own personal take on what the book would say. Plotting sufficient other points, which I think is really ambiguous and really vague and just really not helpful at all. But as you guys write this down, I'm going to go ahead and look in your homework and get the exact wording for how the book states this step. And remember, I'm also preparing you for the future in math. So when I say sign chart, that actually applies to something later. Your book puts it like plotting sufficient solution points. Alright, that's how the book would call it, or describe it, or name it. Plotting sufficient solution points. Plotting means graphing. Sufficient, whatever I think is good. Solution, points for the function given to me. Points. There's not really much of a description in what they would say. There's not really much of a, hey, here's how you actually do it in what they would say. Which is why I'm kind of mapping it out for you and saying, here's what I want you to do whenever you see plot sufficient solution points. Just think sign chart. You don't have to write all this down every time you see these directions. This is just the steps. These are the steps. These are the directions for how to go about plotting the sufficient solution points. But if we know eventually we're getting points, we are going to make a quick table. And the best way that I can show you this is literally just to use the example on the page before. In the page before, you had negative 2x to the 4th plus 2x squared, is that right?
Yeah.
And you guys factored that to be negative 2x squared times x plus 1 times x minus 1. Remember with factors, it doesn't technically matter what order they're in. And then you found the zeros to be x equals 0, negative 1, positive. Okay. I know you have a little number line. Okay? And I know you have a little, you wrote in f of x is positive above the number line and f of x is negative below the number line. Do you know why I said that? What axis is not shown?
The one on
Mm-hmm. The y-axis, where are positive y's?
Up.
Up. Oh, positive y is up, so it's above. And then where are negative y's? Down. Hence why, okay. I'm just saying there's no y-axis, but just remember what's going on. All right. The very first step is mark the zeros of the function on a number line. I call the sign chart, you can call the number line. Mark the zeros, mark the zeros, mark the zeros. Here's what I want you to do when it says plot sufficient solution points. I want you to visualize or even literally write down a number line. I want you to put the zeros of the function on the number line. And now I want you to look at this number line in however many pieces the zeros cut it up into. Meaning, from negative infinity to negative 1 is one piece. So as I move left to right, stop, there's 1. Stop, there's 2. Stop, there's 3. Stop, there's 4. Well, it keeps going. But those zeros have split that number line technically into 4 different pieces. And I want you to choose numbers from each of those 4 different pieces. Like, in this piece, the first one, why not choose negative 2? What's something well, there's infinitely many numbers I could choose, but I don't want to plug in really ugly stuff. What's something kind of basic I could plug in between 0 and negative 1? Yeah, negative 1/2. And most polynomials are kind of symmetric. So let's say if we did negative 2 and negative 1/2, let's also choose positive 1/2 and positive 2. Now here's the struggle, and the book is telling you this when it says plot points. You got to start with x's, and what do you got to find? Yeah. You got to start with x's, and you got to find y's. How do you find y's? Oh, I hear those calculators coming. Sad day. Maybe on a test, if you have a calculator, you could, but maybe on a test if you don't. Wait, how do I raise negative 2? Oh, I can do that, right? F of negative 2.
Oh.
I could raise negative 2 to the 4th power and squared, but where else could you plug it into? Do you have to plug it into that one? Can't you plug it into that one?
Yeah.
Maybe the math would be a little easier. Like negative 2 times negative 2 squared times negative 2 plus 1, negative 2 minus 1. This lets us break it down into little baby math facts, right? Like, can't even talk. Negative 2 times, what's negative 2 squared? What's negative 2 plus 1? What's negative 2 minus 1? How do you do that when you have lots of stuff getting multiplied together? Left to right, just go for it. Meaning, negative 2 times 4 is negative 8, yeah? You want to keep going, negative 1 times negative 3 is 3. So what's my final answer for this first one? Negative 24. Negative 24. Now, 1/2, that doesn't sound fun, but that's okay. Plug it into that factor form. And once again, our math facts are all broken up. So negative 2 times negative 1/2 squared times negative 1/2 plus 1 times negative 1/2 minus 1. Ugh. Maybe I won't write it next to it. It's not in the room. But we know negative 2. Help me out. Do you guys know how to do negative 1/2 squared? And negative 1/2 times negative 1/2 is positive 1/4. A whole take away a half is another half. Negative 1/2 plus 1. There's another half remaining. And what's negative 1/2 minus 1?
3.
Yeah. You could say negative 1.5, or you could make the 1 into a 2 over 2. And say, well, negative 1 minus 2 more halves would be negative 3 halves. Not gorgeous, but we're still getting there. This little negative 2 would be over a 1, right? So you have negative 2 times 1 times negative 3. That'd be positive 6. Multiply all the tops and then multiply the bottoms. 2 times 2 is 4. 4 times 4 is 16, which ends up in a 3 over 8. Here's the cool thing. We can't do this with every function, but we can with polynomials when we notice that it's centered around 0. Do you see how 0 and then the 1 and negative 1, they're symmetric? That's what we can do when we get to 1/2 and 2. If we already know the shape of the curve is something like this. Say, hey, it's symmetric. Guess what? Wait, what? How'd I do that? You already kind of know what the graph needs to look like. Can't you just say, well, wherever it is at 1/2, it's going to be, right? It's going to be the same. And wherever it is at negative 2, wherever it is, it's going to be the same at positive 2. Sometimes there are shortcuts. But technically, you could have kept plugging in and getting the rest of the numbers. What did we just do? We got more than enough to graph. We got more than enough to graph. This entire nasty quartic function, I'm just going to get rid of this because we're not even going to use it. I'm going to get rid of it. This is the one that we've been working with the whole 2 pages. So we can graph our 0, 0, negative 1, 0, negative 2 we have a point for, as we do for negative 1/2. Positive 1 we have a 0, positive 2 we have a point for, as we do for positive 1/2. At 2 and negative 2, we have to go to like negative 24 or something, right? Let's go by 4s. 4, 8, 12, 16, 20, 24. Sure. So we have 1 point. We have another point. Struggle. What's going on at negative 1/2 and 1/2 though? He's only, what, like 3/8?
Yeah.
There's 4, there's 2, there's 1, there's 3. 3/8 would be, holy cow, that like barely goes up. Do you guys see that? Look at him. Funny little guy. He's gonna like barely go up. Keep it smooth. He barely goes up. Got your graphing calculators. Do they agree? You just graphed a cortex. I would dare to say you did it pretty well.
Yeah.
Go team.
How?
Power of magic.
Now question. What would have made this problem so much harder?
If I pulled out a graphing calculator
Okay,
and did it.
if we couldn't factor, that would have been awful. If you didn't pull out your graphing calculator. Well, you didn't need it till the end. What else would have made it awful? What if it had been shifted down, even like just 5? We wouldn't have any zeros. Oh, stink. If we didn't have any zeros, what would we do?
Not do it.
We wouldn't have any intercepts. We would just keep on plotting numbers and hope that we get a nice pretty graph. So, is our process perfect for every single possible polynomial out there? No. But does it at least let us have a clue? Have an idea of how it acts, how it behaves, and what it looks like? Yes, at least a clue. It's not perfect,